So, we were discussing eddy current loss. We will continue that topic in lecture 12, and so we understood no point in using solid block of iron, because there will be so many eddy paths, eddy current loss will increase, because that eddy current loss is in any case is not going to transfer energy from primary to secondary, which is our primary job. It will be locally, there will be heat generated, core will be heated up, and there will be efficiency will be poorer. So, how to reduce that eddy current loss? From common sense, it looked like that instead of using a solid block of iron, you better use thinner plates, stack them together and get the sectional area. Therefore, it is now true that at least I have to use thin plates. Okay. Therefore, in this topic what I am going to do is this: to find out an approximate expression for eddy loss in a thin plate, So, if in one plate I can find out, for all other plates it will be same. So, this is the thing I am trying to get. Acha. To do this, what we will be doing? We have to do a little bit of mathematics, but that is very simple, no field equation, nothing. So, consider a thin plate. Let me draw it here. And this thin plate I will draw slightly larger, although its thickness is quite small. Thickness is of the order of 0.25 millimeter, 0.3 millimeter, but I am drawing it in a larger scale, so that we can understand what is going on. And suppose this is a single plate and it has got a length that side also, got the point. Acha. In this thin plate, what we will be doing? We will make x and y axis. I will assign this to be my x axis, and this is my y axis, and this is my origin. And suppose the thickness of the plate is tau, is the thickness. Now, I have to find out an approximate expression of eddy current loss. To find that out, what I will do is this: I will consider at a distance x from the origin a loop like this, got the point. Let me complete, then I will explain. See, in that within that thin plate, I have considered at a distance x, this distance is x, and elementary thickness dx. Why that dx is necessary will be clear. Our plan is to find out what will be the eddy current induced voltage in this loop, and this loop exists in all the section, here also it exists all along the length. This is suppose the length of that magnetic circuit, whatever it is. If you unfold that core material, that length over which that exists, that is the somewhat the you got the point, length of the magnetic circuit. Anyway, so this is the thing. Now, in this considered loop of thickness dx, what will be the induced voltage, RMS induced voltage in this loop, RMS induced voltage in the loop will be, that is E Eddy is equal to root 2 pi f into phi max. Phi max is what? The flux enclosed by this area, mind you. But that flux enclosed in the area can be written as B max, which is calculated over the whole cross sectional area root 2, that phi max divided by overall area, root 2 pi f B max into the cross sectional area, that is this blue hatched area. What is that area is? This is 2 x at a distance x I have taken. So, 2 x into, suppose this is the height, I just call it h here, into h. So, root 2 pi f B max into 2 x into h, it is phi max into number of turns, that is 1. Therefore, eddy power loss in this loop will be equal to, if you neglect reactance of this loop, only resistance single turn. So, E Eddy square divided by resistance of this path. This will be the power loss, V square by R, what else, because the circuit is closed. Therefore, this I will write it now, I will just put these values. It will be 2 pi square f square B max square into 4 x square h square. Now, the question is, what will be this resistance? So, resistance of a path, I will apply that basic formula rho L by A. Rho L by A. Now, the question is, what is rho? Rho is the resistivity of this core material. Rho is resistivity, so rho. What is L? L will be how much? The length of this path, current path. It will be 2 x plus 2 h, perimeter of this path, divided by the cross sectional area through which this current is flowing. Now, what is the here it requires some observation, that is, what is the cross section? This loop, as I told you, exists all along this length, here also it exists. So, and current at a given instant of time will flow, this is the cross sectional area, because the loop exists here also for all the, this is not for this single fellow. Loop is positioned at a particular x and it is here also, and current, eddy current path will be what? It will be perpendicular to this area. Got the point? So, rho L by area will be then the area of this rectangle. What is the end of this rectangle? The length of this iron piece. And this will be then, if I call this length to be L, which I wrote earlier, suppose this length is L up to whatever distance it goes. So, this is L into dx, L into dx. This is the cross sectional area. Therefore, this is the thing. Achha, now, you see, as I told you, we would like to find out an approximate formula, okay, to have a feeling on what factors eddy current depends, like that. Now, since it is a thin plate, the value of tau is much smaller than your this finite dimension h or L, whatever it is. The first assumption is this one, this equal to, I will write it as it becomes 8 pi square f square b max square h square x square. This is this thing divided by this one, I will write it as, this is approximately equal to this 2x. See, x is a subset of tau, tau is already small compared to h. So, there will be no harm if you write it as rho into 2h. This 2x term can be neglected compared to 2h, divided by L dx, which I will put up like this. Is that clear? So, this then will be equal to 4 pi square, this to max 4 pi square f square, oh my god, b max square into h square, no, h, one h goes out. So, h it becomes h and then x square into L into x square dx. It is now a manageable expression and divided by rho, of course, is not. So, this will be this loss. So, this is I will say this is dp eddy on this elementary loop, okay. And this portion I will just copy it and carry on. Okay. So, we got from the previous slide, this is the thing. Okay. Therefore, this is the thing. Now, the question is how to get P eddy total. So, P eddy total in that plate, it will be equal to these are constant 4 pi square f square b max square into h into L, and this is x square dx, and this is to be integrated. So, I go to previous page. The question is, what will be the limit of integration? See, at a distance x, I have considered the full loop. So, 0 to t tau by 2 will be the limit. This is tau by 2, where tau is the thickness of the plate. So, that will be the limit. So, 0 to tau by 2, that is all. This will be the thing, divided by rho, of course, is there. So, next step is straightforward. What you do, 4 pi square f square b max square h L x cube by 3. So, it will be tau cube by 8 minus 0, and this is by rho. Is that correct? Into 1/3 x cube by 3 into 1/3. So, this is 1 by 6 rho pi square f square b max square and h L. This tau cube I will write it like this, h L tau into tau square, and then I can write it as 1 by 6 rho pi square b max square f square tau square into h L tau is the volume of the iron, volume of iron. So, the P Eddy total is given by this. Now, going to the previous page, you also notice I have assumed another thing. When I varied, I have considered the loop not like this, but it covers, as you vary x, it covers the whole area, then you are through, okay. But not only that, when x varies, this portion remains same, as if I have calculated many times that area. But anyway, I have whatever I am estimating, I will be estimating slightly higher, it is no harm. So, there is another approximation. Are you getting another loop you consider? You will consider it like this. Okay, this power loss here, and once again this power loss, but that portion is always small, because I am talking about tau, which is far less than h. Therefore, this is a very handy approximate expression, mind you, approximate, it will serve my purpose, approximate expression. For eddy loss, and I know many things. Eddy current loss then depends upon the maximum value of the flux density squared, supply frequency squared, and thickness squared. Remember, what is the fun of expressing it in this way? It is because of the fact I have considered while deriving this with a single plate. There will be multiple plates, and I know it can be expressed in this way. Therefore, if you have used more number of plates, then total volume is to be multiplied. Are you getting? That is also crucial to note. So, I will say better write P eddy power loss per unit volume is equal to 1 by 6 rho, sorry, one by 6 rho pi square P max square f square tau square per unit volume, per so many watt per unit volume, watt per unit volume. And we say that then eddy current loss will be proportional to the square of the thickness of the plate. See, all these things, the argument was, if you use a solid block of iron, eddy current loss is bound to be more, so many eddy paths. Instead of that, you use the eddy currents, it will be only confining here, because the next plate is insulated from the other. If you do not use insulated plates, then the story remains same, the eddy paths will be more. Are you getting? That is why the insulation is necessary. Therefore, we know that. So, how to reduce then eddy current loss? Because it is a wasteful energy. Transformer will be on 24 hours, okay? And eddy losses will always take place. If that be the case, you try to use such a material whose resistivity is higher. Rho should be made higher, at least this is apparent. Use small tau, that is one factor, thickness of the plate should be tau. It cannot be too small, otherwise those thin plates you cannot further make it smaller and smaller, it will become then brittle, you know. So, the order of the thickness used is maybe 0.25 to 0.5 millimeter for 50 hertz transformer, tau, order of tau. And transformer size, if you see, they may be of the order of a distribution transformer. If you look at, their heights may be in meters. So, the assumption that H and del compared to those values tau is very small is pretty good, I mean nothing like that. But it gives, so do not use just iron, try to use a better material, that is why people use steel, silicon steel. Add some small quantity, exact percentage I don't remember, you can see a design book, add silicon to ordinary iron steel and make a special type of iron which will give you higher resistivity to reduce the loss. And also try to do not try to use too high a Bmax, which will also reduce. And remember, it is proportional to frequency square. So, if the transformer rating is 50 hertz, based on that you try to make eddy loss as small as possible. So, please remember what was the logic, why this was necessary to derive. It was necessary to derive because in the transformer, if you go to this previous page as well, previous page. See, in this transformer, therefore, what I am telling, if I spoil this page, after this I will tell it like this. It has come. There. This is the thing. So, finally, it will look like this. Instead of a solid block of iron, I will use thinner plates. So, this I am showing it by lines. Another plate, another plate, another plate. I think you have got the ideas of this kind. Got the point. So, many plates like this, you stack them together and try to form a core material like this. These are also called laminated plates. Use laminated plates. In short, it is called laminations, each plate, laminations. Then you make your winding not over a solid piece of iron, but like this. Another side it is like this, make your primary and secondary. So, eddy current loss, it depends on Bmax square, F square and thickness of the plate square. Thickness should be 0.2, 0.3 millimeter thickness, and each plate is insulated from the other, and this will be also reflected here in this drawing. I think this is okay. So, and this is the flux. Total flux is phi. By this area, the cross sectional area, if you look at from the top, it will be now like this, and your phi is coming like that. So, average flux density is Vmax divided by, because each plate will contribute to the area that is there, that overall area will give you the Vmax. Anyway, so far so good. So, this is called eddy current loss. Now, how to take this eddy current loss effect into the equivalent circuit? Coming back to the original question. So, it looks like that even with the secondary of the transformer opened, I mean you can look at it in this interesting way as well. This is V1F, you have switched on the supply, secondary is open, nothing like that, but there is core material. Now, when you close it, there will be phi produced, alternating phi t is produced, which is flowing like this, and there are eddy current losses. You can also think, oh, then I have applied the voltage, and in the core there were turns existing, they had induced voltage in the same way as your secondary coil had induced voltage, and they were driving current. You can also think like that. Okay. That is what I am trying to tell. Even with this switch open, it looks like as if there is a secondary coil existing within the iron core, they are, and the circuit is closed, they are carrying secondary current. But flux has to remain same. Therefore, those tiny eddy currents too will have reflected current on the secondary side. I mean, what I am trying to tell, I mean another way of looking at the thing. This is your voltage, okay? And suppose only eddy current I am showing, the flux will be around this point phi. There is induced voltage in the secondary too, that is there. But what I am telling, there are some invisible secondary already present in the core, and they had induced voltage also in the same direction. Why not EAD? And I assumed that power factor of that eddy current path to be unity, leakage inductance. Therefore, with secondary open, there is no I 2 here, that is fine, but here was a secondary, it had I eddy, and why not it will have its reflected component here, in order that your flux in the core remains same. Therefore, apart from this magnetizing current I m, we now find there will be an current due to core loss, which will be in phase with the supply as it is expected. This is how this current will be drawn in. Another way of interpreting the result. Got the point. But anyway, what people say is that this eddy loss, after all the power has to come from this, therefore, there will be another small component of current drawn from the source, which must represent eddy current, that will be in phase, can be physically interpreted like this. Now, after I have done this, I will come to this complete phasor diagram slightly later. Before that, I will tell you something about another component of the portion, that is called hysteresis loss. Okay. What is hysteresis loss? Hysteresis loss is another loss which also takes place in the core, takes place in the core, like eddy current loss. Now, what is this loss? This loss is slightly I mean of the track type things, but we know why hysteresis loss should take place. See, after all, if you have a magnetic material like this, over which you wound a coil, and are you getting? So, suppose let me draw some coil, say a piece of iron, and here is a coil. Like this, a coil is wound and this length is more, whatever it is. And suppose you pass current in this way, some AC current, connect current, some AC current you pass. If you pass current, then why this core gets magnetized? It is because of the facts, we will not go to the quantum level, but we can understand there are tiny magnets, molecular level, small magnets are there in any ferromagnetic material like this, north south, but they are, see, north south, they are tiny magnets already existing in a ferromagnetic material. So, what you are doing, the moment you apply some, I will draw now sectional diagram. If you pass some current like this, so inside this there are tiny magnets which are haphazardly oriented and we do not see any magnetism in it. But if you pass some current, some DC current you pass to this fellow iron bar, that is how I make permanent magnets, you know. So, you pass some DC current, therefore, there will be, you have applied H along this, and each tiny magnets will try to align itself along NS, all the magnets. If you pass a little current, they will slightly move and pass more current, they will be further aligned NS, make it more they will school level also we study like that. So, if you pass sufficiently large current, at the end what will happen is S n, all tiny magnets will be moved like this, such that this will become a north pole and this will become a south pole. That is how we are taught in school level how to make a soft iron piece a permanent magnet. You pass some electromagnet north south. Okay. Now, suppose this current is time varying. Therefore, what you are asking each molecule to do, if this is time varying, when the current is positive, each tiny magnets was trying to align along this way, then you reverse the current, they will now start moving, and finally, when the negative maximum current flows, this side will become south, the other way it will become, it is north, it is south, it is north, it is south, I am just drawing, is not. So, each one will move and finally, they will align, provided you reverse the direction of the current. I am not drawing all this, these are very basic. Therefore, if it is a 50 hertz frequency current changing, then you are asking each molecule to move this way, then that way, always they will be moving. Therefore, they will encounter friction in the process and there will be heating effect, not because of eddy current is separate thing, but simply because you are reversing the currents this way that way. Therefore, there will be always movement of the molecule. That way you can imagine whether exact thing, perhaps detailed analysis of at physics level you have to do, but we can understand, okay, this is what is going to happen. Each molecular level tiny magnets, they will be sometimes aligned this way, sometimes this way. Therefore, core will be heated up not only because of eddy current, but because of something else here. And this loss which will take place is called hysteresis loss, and we will continue with this in the next lecture. Thank you.